Welcome, diploma students. Today, we're jumping right into the absolute must-have toolkit for any modern automation engineer. We're going to take a structured academic look at the 5 primary programmable logic controller, or PLC programming languages, and see exactly how they architect the industrial world around us. So let's start right at the foundation, the IEC 6131-3 standard. Now, prior to 1993, PLC programming was honestly a bit chaotic. It lacked standardization and relied heavily on proprietary vendor dialects. You basically had to learn a completely new language for every brand of hardware. But this international standard brought some much-needed order to the industry by defining a unified software architecture and a standard suite of 5 programming languages. Here's our agenda for this explainer. 1. The IEC 61313 International Standard. 2. Graphical languages. 3. Textual languages. 4. Sequential function charts. And 5. The future of industrial automation. Let's dive right into Section 1, the IEC 611313 Standard Basic Concepts. What's really fascinating here is how the standard organizes control paths using Program Organization Units, or POUs. Basically, a resource hosts tasks, and those tasks execute programs. And these programs, well, they're essentially networks of highly reusable function blocks. This modular approach is a total game changer. It allows you to encapsulate complex algorithms, like a PID temperature loop, for example, and just reuse them across multiple projects without having to rewrite the code from scratch. And we absolutely can't forget about strict data typing. By categorizing data into specific formats, like a simple 1-bit Boolean for an on-off switch or a 4-byte real floating point for super precise analog measurements, this architecture prevents fundamental logic errors. You literally can't accidentally divide a date by an integer. It ensures the strict operational rigor that heavy engineering absolutely requires. Moving on to Section 2, Graphical Languages, and taking a visual approach. First up is the ladder diagram, or LD. This actually started out as a physical written method to document the design of relay racks in manufacturing. Ladder logic was deliberately designed so that factory engineers could easily transition from hardwired relay systems over to software. They didn't have to go back to school to learn complex procedural computer science languages like C or Fortran. It simply reads left to right, evaluating contacts to energize a coil on the right side. Now, the real takeaway here is the contrast between our 2 graphical options. Ladder logic is fantastic at discrete, rule-based loop execution, checking if a stop button is closed and a start button is open. Function block diagrams, or FBD, on the other hand, are incredibly common in the process industry. FBD uses elementary blocks wired together to map the continuous flow of signals. That makes it perfect for analog systems where you're tracking data moving from an input, going through some math function, and then heading out to a control valve. All right, on to Section 3, Textual Languages, focusing on code programming. The standard gives us 2 distinct textual tools. First, structured text, or ST, which gives us a high-level Pascal-like syntax that's absolutely ideal for complex decision-making and data arrays. In contrast, we have instruction list, or IL. This offers a low-level assembly-like structure, which was historically favored because it has a tiny memory footprint and incredibly fast execution on early microprocessors. You'll find that structured text is rapidly becoming an industry favorite, especially as control systems get more and more data-centric. Because it supports advanced logical branching like if, then, and case statements, it's perfect for state machine emulation and complex math. It executes just as efficiently as ladder logic, but remained highly readable for programmers coming from a computer science background. But here's a vital piece of history. Instruction lists, despite being hugely important for memory-constrained embedded controllers back in the day, is actually officially retired. It was deprecated in the 3rd edition in 2013 and completely removed in the 4th edition coming in 2025. It just goes to show how industrial standards really have to evolve alongside modern hardware capabilities. Section 4, Sequential Function Charts, Managing Sequential Flow. Sequential Function Chart, or SFC, is honestly way more than just a language for writing equations. Think of it as a structural blueprint. Based on Petri nets, it helps decompose massive, complex batch processes, like a complicated chemical mixing sequence, into clear, manageable, isolated states. It's an inherently parallel programming tool that lets you see exactly where a machine is in its operational cycle at a glance. The way SFC execution flows is incredibly logical. The system rests in an active step, executing a specific action, like filling a tank. Right below that is a transition, which is a logical condition, like a level sensor activating. Once that condition is true, a directed link seamlessly deactivates the current step and triggers the next one, effectively replacing those old complex relay interlocks. Finally, Section 5, the future of industrial automation and combining these languages. Here is perhaps the most important lesson for you as future engineers. A modern automation engineer doesn't just stubbornly pick one language and stick to it. Thanks to the IEC standards' common elements and data types, you are actively encouraged to mix and match these tools. You'll probably use SFC as the structural backbone of your machine, write your discrete safety interlocks in ladder logic, use FBD for your continuous PID control, and rely on structured text for the heavy data crunching. It's all about applying the perfect language to each specific control problem. By mastering this toolkit and understanding the specific strengths of each, you are totally prepared to architect the automated systems of tomorrow. But as legacy systems fade out and the demand for data-heavy, object-oriented programming rises in the era of the industrial Internet of Things, which of these languages will you rely on most in your career?